Okay. Well, I've heard it said that a lecture is a situation in which information is transferred from the notes of a professor to the notes of a student without passing through the brains of either. And right now, being the end of the day on a Monday, at least on my side of things, that's exactly what's going to happen. So, that I'm just gonna look at these. It's like, oh, okay, I'll just go with whatever's here. Also because, well, we have 3 weeks left.
Oh, don't say that. That's crazy.
I thought that'd be a good thing.
Well, there's so much to get done in 3 weeks.
Well, yeah, I guess that's true with the homework in this class. Yeah, and I still have a fair amount to cover. There's the rest of chapter 4. And then chapter 5 is kind of optional-ish, but in terms of its relation to the homework, but it's also important stuff. So we'll just see how. So that's my rhythm here to do this on Mondays, and then okay. Okay, so this chapter is all about the time-independent PDE, the Poisson's equation, and how we solve the system of linear equations that comes from it. Now, when I covered section 4.1, that was really about how we get the system of equations from a PDE in the 2D case, whereas 1D case had been covered previously. And different possibilities, like in 2D, you could have the 5-point stencil or the 9-point stencil for Laplacian, and a different local truncation error that results, and how we use a Kronecker product to go to higher dimensions quickly in MATLAB. So the remainder of this chapter is how to solve this system once we have it. Now, even though that's something we all learned about in our first linear algebra class, how to solve a system of linear equations like this, but with the computer doing the work, things that are meant to simplify our lives can actually complicate them considerably. So I'm going to cover various methods for solving this kind of system, because it is a large system of equations and sparse. Most of the entries are 0, which is something that ought to be taken advantage of. You certainly want to take advantage of it from a storage point of view, but also it means that Gauss elimination is likely not to solve it. Okay, and the funny thing is about something we take for granted, like Gauss elimination, is it had been used for such a long time, invented by people other than Gauss, and taken for granted as the way to solve systems. But once computers came along, well, okay, I have to be careful about my use of words computers when I'm talking about what happened long ago. because back in the earlier 20th century, computers were not devices. It was an actual job title. So agencies such as the Department of Agriculture would employ people as computers. They'd sit at a desk all day long and solve systems of equations based on like crop data and so forth. And so they had to really know their elimination and such. And then when electronic computers came along and they would implement algorithms such as Gauss elimination and back substitution on them, they were actually quite concerned because now floating point arithmetic was an issue and the error that comes from that. And there are some researchers from that time, 50s, 60s, well, I guess really 50s, who were actually convinced that Gauss elimination was not viable on an electronic computer. They thought it was numerically unstable, that the round-off error that would accumulate when solving a large system of equations like these would just be unacceptable. And it was Jim Wilkinson who wrote really the authoritative work on eigenvalue problems. It's called the Algebraic Eigenvalue Problem by Wilkinson. It has all the secrets in there. Actually, I should have you guys look at that because you deal with eigenvalues and eigenfunctions. But another great contribution of his was he proved through a very careful and tedious round-off error analysis that Gauss elimination with pivoting, that's very important, with pivoting is numerically stable. That the error in solving a system could be bounded to a reasonable degree. And therefore Gauss elimination was accepted at that point. But yeah, they're almost like, nope. I'm not sure what they would have done instead, to be honest, because, you know, well, we're going to see some other methods, like iterative methods. And those are very widely used today. That may have been the only way. Okay. So, first type method I will talk about, direct methods, which involves elimination. Gauss elimination and its close relatives. Okay, now, I would say this is a review of 461, 561, but only one of you in this room has taken that. So it's not really much of a review. Well, I guess for you it's a prophecy. So, for foreshadowing, really. 461, 561. So that you're taking next week. What?
Is that real two?
Numerical 2. Yeah. Although, well, actually, this would have come up in 610 also. So, but I cover more in depth there. Okay, so we're solving a general system of equations, AX equals B. Please do not be like I heard about from my friend at, of all places, Stanford, who actually thought that these were completely different problems, just because of the choice of letters. They came up to upset after the midterm, like, don't all supposed to go along about how to solve AX equals B, and then in the exam you had CX equals D. Don't be that student. Okay. Well, but again, they were mechanical engineering, so I guess we should be understanding. So what happens is, here's the process, a 3-stage process. We do Gaussian elimination, with some kind of pivoting, most likely partial pivoting, just because it's the efficiency. And that gives you a factorization, PA equals LU, where P is a permutation matrix, when multiplied on the left, it rearranges the rows of A, because sometimes in Gauss elimination, row interchanges are necessary. So you avoid dividing by 0, but here they're also intended to reduce the accumulation of round-off error. So even if it's not absolutely necessary to interchange, partial pivoting still does. And then L is there's my symbol for a lower triangular matrix, and U is an upper triangular matrix, because triangular systems are far easier to solve. And this takes roughly 2/3 n cubed. I've been using uppercase n all this time, so I'll stick with that. Flops, which I've used that term in some classes, but I don't think I've used it in this one. Floating point operations is a flop. Okay, that's the most expensive part. And then we do forward substitution. So that's where you solve the lower triangular system. Ly is equal to PB. And then, and that takes roughly n squared operations, so much cheaper. And then we do back substitution. So that's Ux is equal to Y. And that takes also roughly n squared operations. Okay. And the easiest way to see why this works is if I go back to the original problem, multiply both sides on the left by P. And then replace, oh wait, that's not right at all. Okay. Then we replace PA with LU. And then denote UX by Y. Then we see Ly equals PB, UX equals Y, PA equals LU.
Wait, what's that for? That's for Gauss elimination?
Yes. Yeah, all of this is Gauss elimination. Okay. I should mention that when I give these operation counts, these are of a general case, where A could be any matrix whatsoever. But when a matrix is the kind of sparse matrices we've been seeing, where we only have a few non-zero diagonals, like 1, -2, and 1, a tridiagonal case, or even a two-dimensional case that has other non-zero diagonals that are further apart. All these operation counts become order n, just because the matrix is so sparse. Okay, so actually I need to fill that in over here. So specializing to this system, we have these things to take into account. All right, just because of the sparsity. But especially in higher dimensions, Maybe a problem with pivoting. That when you're doing partial pivoting and you swap rows, you might end up introducing new non-zero entries into the matrix that were zero before. The matrix becomes less sparse, which interferes with this goal of having greater efficiency. Do anyone know what it's called when you're interchanging rows and that makes the matrix less sparse? Okay, well, would have been mentioned a long time, not in this class, long time ago. So, well, it's been at least, since spring when you heard of it, and longer ago for you.
Making something less sparse.
Yeah, so introducing new non-zero entries. What?
It's not substitution, or
Is it discretizing?
What?
Is it discretizing?
No. Discretizing is how you get the system from this. Fill-in is what it's called. What? Oh, okay. So people have developed alternatives to partial pivoting for these kind of matrices that relax the requirements of which rows get swapped with which rows to try to preserve sparsity. But it's a big problem. That's another reason why I mentioned last time when I was covering a previous section about red-black ordering to get a new system of equations. So that's one way to get around this issue of so you're not having to pivot quite as much. Okay, now aside from that, there's some variations of Gauss elimination that I need to mention. Okay, so if A is symmetric positive definite, or SPD. Which is the case if A is meant to discretize minus Laplacian. Minus Laplacian is a positive definite differential operator when you have Dirichlet boundary conditions. So discretizing will lead to a symmetric positive definite matrix. You can use this, and actually can be proven that you never have to pivot. Although it might still be a good idea. But there would never be a threat of dividing by zero when it's SPD. But it's still not the best way to go. There are two direct methods for solving a symmetric positive definite system. Can anyone name either of them? Those have come up in this class.
Cholesky.
Yes. Cholesky factorization, which has this form: A is equal to GG transpose, where G is lower triangular. So now you're still solving a lower triangular and upper triangular system by forward and back substitution. But now the factors are transposes of each other. And for a general case, this is roughly 1/3 n cubed floating point operation. So it takes half as much work as Gauss elimination just because of the symmetry. So that's why it's a good idea. There's one other that's very similar to Cholesky, the LDL transpose or LDLT factorization. It's also 1/3 n cubed. They call LDLT the square root free Cholesky because the Cholesky algorithm does involve computing some square roots, whereas LDLT doesn't. In fact, what you could say is G from Cholesky factorization is equal to L times d to the 1/2. Now L is a lower triangular matrix, just like the L in LU factorization, Gauss elimination, whereas D is a diagonal matrix. So positive entries in a diagonal, 0 everywhere else. So it's very easy to take a square root. You just take a square root of a diagonal entries. So the two are very closely related. Okay, I should mention. Okay, how do we do all these in MATLAB? Let me make sure I have my function names right. Okay, so in MATLAB, if you're doing Gauss elimination, that's this backslash. So using a backslash, like A\F, what you've done on the homework, that performs Gauss elimination with partial pivoting. If you want to do Cholesky, so there's the Chol function, CHOL, that computes the Cholesky factor. I should mention, though, the Cholesky factorization is written in different ways. I like this format where it's always lower triangular times upper triangular. So I write it in this form where the second factor is transposed. But MATLAB does A equals R transpose R, where R is upper triangular. So it outputs the matrix R, which is the same as G transpose. It's just a notation thing. And then you can solve your upper and lower triangular systems with that using backslash, because backslash is a very intelligent operator. If you use backslash with a matrix that's already triangular, it will detect that. And it won't do elimination again. It'll actually go through the substitution process directly. And then finally, for the LDLT factorization, function for that is LDL. That actually is a lowercase l in both cases. I'm not writing the absolute value of d. Even though I just realized, yep, it really looks like that. Okay, so that would return the L and D factors that you can work with after that. And the thing is, I mentioned this algorithm uses square roots. There's not many of them. It can use n square roots. And it's easy to think, oh, we have addition, subtraction, multiplication, division, square root. It's all the same. No, it is not the same at all. First of all, multiplication and division are far more expensive than addition and subtraction. Even though they're counted as a single flop because there's one use of a circuit. But those circuits are a lot busier for multiplication than addition. Because in addition and subtraction, only corresponding digits interact, except for a little bit, or there's borrowing or carrying. Whereas with the multiplication, all the digits interact. So it takes an order of magnitude more work for that. That's why anytime an algorithm can be written in such a way that it does additions in exchange for multiplications, that's a good thing. But also, what about an operation like square root? To us, it's kind of a black box. It's a button on your calculator. Or in MATLAB, you're typing SQRT of X. But there's no circuit to do square root. It has to do an approximation using something like Taylor series or Newton's method or something like that. And that so something like a square root or an exponential would require several floating point operations, and that can really add up. So use of such functions wisely. And these are things that programmers way back in the beginning of electronic computers cared about a lot, because each operation was not very fast, and they didn't have a lot of time. So they would write their code such a way that they would multiply by 1/2 rather than divide by 2, because divisions were a little more expensive than multiplication. And these days we're like, eh. But we're also requiring computers to perform trillions of operations, and more of them per second. So in other words, all that stuff still matters. It's kind of like with big data. Ever since people started yakking about big data, they're like, oh, we don't need statistical techniques anymore. We have computers that can process all the data. And like, no, you still need all that stuff because you just have a larger scale version of what you had before. But people get crazy about these kind of things. Okay. Now, and this is why I go on about this, because I was not around for the old days of numerical analysis, but I heard plenty about it, from my advisors and professors and so forth, and that stuff really shouldn't be forgotten. So I've given you a chance to forget it. So, but it's better than never knowing it at all. Okay, so those are let's see, direct methods. Okay. Oh, okay. Actually, the next thing is about sparsity and fill-in, but I already talked about that. Okay. I do want to say a little more about pivoting, rearrangements and all that, and also the structure of a matrix. Okay. Okay. So, on the one hand, pivoting is important to reduce round-off error, accumulation of round-off error. But pivoting can destroy sparsity. So how do we balance these concerns? So how do we avoid fill-in while still getting the benefits of pivoting? So one tactic I already mentioned, that in certain cases, red-black ordering. So that's a way of rearranging rows and columns. Okay. To basically decouple the system into two smaller systems. And that remain sparse. Now, this is for matrices like minus Laplacian. But you may have other matrices that come from a PDE that do not have such a nice structure, so red-black ordering may not help. So what can you do? So this technique is effective, but it's very limited in the cases you can apply it to. Okay, so what can you do instead? There's some MATLAB functions that can help. Call AMD. So what this does is returns an ordering of the columns. Really, it gives you a permutation matrix, but so that's something you can multiply by A on the right to rearrange columns. To preserve sparsity, even after doing pivoting. Okay. All right. So in other words, it makes sure that the L and U factors are more sparse than if you didn't do anything. I'll have to confess, I actually don't know how it figures it out, or I don't know if it's optimal either, but it's something that can help. Now, what about when your matrix is symmetric? When the matrix is symmetric, here I've talked about rearranging rows for Gauss elimination and pivoting. Function like call AMD will give you a way to rearrange columns. How come? What's the really bad thing about if I rearrange rows of a symmetric matrix? What do I lose by that?
Darn.
What?
If you rearrange the rows in symmetric matrix,
Yeah.
it's not symmetric anymore.
Yes, you lose symmetry. Yeah. So what you do is you take it a step further. Rearrange the rows and columns. So if you apply the same interchange to like rows I and j, and then columns I and j, that will preserve symmetry. Because if I have matrix A, and multiply in the left by P transpose and the right by P, the result is symmetric. So that's equivalent to applying the same row interchanges to the rows as to the columns. MATLAB has a counterpart to call AMD for general matrices. It's called Sim AMD. So that gives you a permutation matrix to rearrange the rows and columns, so that so also to reduce fill-in.
Is that AMD or AND?
AMD. AMD is approximate minimum degree. Okay. And apparently it's not necessarily optimal, but it gives us an efficient way to try to at least reduce fill-in. Maybe not by the most possible, but it'll certainly help. Okay. Oh, I actually know one of the guys who developed this. Tim Davis, who he was at University of Florida. I think he's somewhere in Texas now. He's like the sparse matrix person. Actually, I think the features in MATLAB that deal sparse matrices are largely due to him. So he just knows everything about them. So he helped develop this. Okay. By the way, I should mention that there's something I did some reading about. This happened about 5 years ago, I guess. The reason he and others left University of Florida is used in the computer science department, and the administration there, led by some malevolent, power-hungry dean, basically wanted to get rid of that program, or at least totally cripple it. Because there's just a lot of upper administration nasty politics going on. And I remember seeing a lot of petitions about saving Florida's computer science program. I think he maybe wanted to absorb it into something else or whatever, but there's a lot of favorites playing going on. And really a lot of damage was done. So faculty like him were just felt like they were being pushed out, so they went elsewhere. Unfortunately, it's one of those things that happens. Because I've been here 10 years, and in that time there have been 3 presidents, 3 provosts, 4 deans of a college, 4 chairs or directors of math department or school of math. That's a lot of turnover at the top. And those people have a lot of power. And all it takes is someone coming in at that upper level and deciding to just go ahead and change things. And someone down at my level who was perfectly content before now has stuff to deal with. And I think that in my position, I'm more insulated than others. But someone like, take Tim Davis, for instance, he was a full professor. And just got kind of blindsided by all that. So, what can you do, unfortunately? Okay. Well, wasn't expecting that, but we're going to have numerical PDEs and other life lessons. Okay. So, next thing to look at is still on direct methods. It's preconditioning. Although, really, those are useful for both direct and iterative methods. So the condition number of a matrix A is, so this is kappa of A, so that's my funny looking K here, it's supposed to be Greek letter kappa, is the magnitude or norm of A times the norm of A inverse. And because you're taking the norm of each, you cannot cancel the A and the A inverse there and get 1. So the reason why this is of interest is if this quantity, this number is large, in other words, we say A is ill-conditioned. The solution to AX equals B is very sensitive to round off error, and say etc. Like changes in the problem, like a small change in the problem could cause a large change in the solution, things like that. So we don't like ill-conditioned problems. And the thing is, ill-conditioning will affect any method that you might use, because it's not a property of the algorithm you use to solve a system. It's a property of the underlying problem you're trying to solve in the first place. Now, here's the unfortunate thing. When your system, AX equals B, comes from a PDE, so by way of spatial discretization, we can count on it being ill-conditioned. Okay. Also, the condition number tends to increase with a quantity normally referred to as capital N, the number of grid points. So the finer your spatial discrimination, the smaller your delta x, therefore more realistic your model, the more ill-conditioned it's going to be. And the problem is, and conditioning has been known about for quite some time, but back when the concept was first introduced, system of equations were not very large because computers could only handle so much. Now, when they're trying to solve systems involving literally, I think, up to billions of equations now, on the most powerful supercomputers, the net condition number is going to go through the roof, which adversely affects whatever methods you might be using. It can slow things down, and this is something I don't think we're as well prepared for as we'd like to think we are. And this is something I care about deeply for, time stepping methods for PDEs, which is basically a justification for my whole research program, and why I try to take PDEs and decouple them into smaller problems by finding eigenvalues and eigenfunctions and so forth to get around all this. And the thing is, people think, oh, our computers are getting more powerful, they can handle all this. Yes, but the problems get harder. So we have to keep pace with that. So what can we do? Fortunately, there are some things we can do. To make our systems not so ill-conditioned. Okay. Sorry, just making sure that I didn't crop anything off. Don't want Billy missing anything when she's watching at home. Okay, so solution. I put solution in quotes because it's really not a solution. It is not a cure. It's basically a Band-Aid. It's called preconditioning. So the idea is, there's two types of preconditioning, left and right, and you could use both together. So in left preconditioning, all you're doing is you're multiplying both sides by some matrix P inverse. So that hopefully this matrix is closer to identity. Identity is a matrix whose condition number is 1. That's the smallest a condition number can be. So identity is perfectly conditioned. Orthogonal matrices are also perfectly conditioned. So we try to achieve that. Now, right preconditioning is similar. Okay. Solve this system. A times P inverse Y is equal to B. And then you solve Px is equal to Y. So this right here is X. Okay. So you can do both. You can use a matrix like P1 as a left preconditioner and then P2 as a right preconditioner. Either case, you're trying to make a matrix of a new system to be roughly identity.
Is that similar at all to like the difference between forward and backward substitution? Or like, does it matter left or right? Like why is one left and one's right?
Oh, just because if we're multiplying with A on the we're multiplying by A on the left or right. So
But A is on the left both times.
no, like here, the matrix we're multiplying A with is on the left, and here
It's
on the right.
Like,
oh, it's on the right side of A.
Yeah.
Okay, I'm thinking of like the equation.
Oh.
Okay. Never
Okay.
mind.
Right. Oh, yeah. I see what you mean now.
Uh-huh.
Okay.
Yeah. Okay.
Okay. Yeah.
I don't know. I'm just saying.
All right. Now, here's an example of a simple example where preconditioning can be seen to help. All right. How am I doing on time here? Oh, good enough. So let's suppose A is this matrix: 1, 1, 1, and 1,000. So the condition number, which you can compute in MATLAB using cond, C-O-N-D, for a condition number, turns out to be 1,001. Okay. So here's so a very simple-minded preconditioner is just take the diagonal, 1, 0, 0, and 1,000. So the condition number of P inverse A. So if we use this as a left preconditioner, actually cut down quite a bit. Yeah. And if only it was that way all the time, but it's not. Okay. So, how do we choose a good preconditioner? What's a criteria? What makes a good preconditioner? Because notice, one criteria I mentioned is you want a transform matrix to be approximately identity. So that would suggest choosing P to be close to A, because then A inverse A would be identity. But implicit in these equations is another criterion. Because notice I have P inverse B, and here I have P inverse Y. So I have to solve another system. I'm already trying to solve a system involving A, but now I have to solve a system involving P also. So, so that means that, well, and things, I don't want to add a ton of expense by preconditioning. So these systems I solve, like solving, it could be P inverse B or P inverse Y, those systems have to be easy to solve. So my criteria is, okay, so P inverse A should be identity in the case, roughly identity in the case of left preconditioning, or A P inverse should be roughly identity in the case of right preconditioning. So that suggests, in either case, P should be some approximation of A. But the other criterion is solving a generic system, using different letters here to make it generic. Solving any system involving P as a matrix must be easy in some sense, or at least efficient. More efficient than solving the original system. But what does that suggest? That suggests that P should be roughly identity. So unfortunately, these two criteria compete against each other.
If A isn't already close to.
Right. Yeah, the thing is, if A is already close to identity, we don't need preconditioning. So Yes, so if we choose this, we don't have a system easy to solve. If we choose this, then we don't gain anything. The system is still just as ill-conditioned as it was before. So we had to try to find some balance between these offsetting criteria. Okay. How many pages do I have left? Okay. So some examples of preconditioners. If I break down A as a sum, D plus L plus U, where D consists of a diagonal of A, L is the lower triangular part, and U is the upper triangular part. Now these do not include the diagonal, because the diagonal is over here. Okay. Here's what we could do. We could choose P equal to D, just the diagonal part, which is basically like the example I just showed you. And we've seen that at least in some cases that could be effective. Or P equals D plus L. So in other words, the lower triangle of A. So these systems are definitely easy to solve. A diagonal system, you're just forming n divisions. Here, this is lower triangular, so you can use forward substitution. It's still cheaper than solving the original system. Now, whether these are effective as preconditioners, it depends on the matrix. So these are particularly effective if A is diagonally dominant. What I mean by that is each diagonal entry is greater than the sum of all the off-diagonal entries in the same row. So the diagonal entries are ones that are dominant within their row in terms of size. Okay. And those matrices do come up in PDEs. For example, the matrix that we work with a lot has a -1, 2, 1, -1. I can't say it right. -1, 2, -1 for negative Laplacian. So it's not strict diagonal dominance. The diagonal entry is at least equal to the sum of the off-diagonal entries. And then in the first and last row, it is greater. So it's not strict diagonal dominance. But so for something like that, these preconditioners would be helpful. Okay. Now, another approach. Okay. You can let A be approximately equal to L tilde U tilde, where let's suppose that all three of these matrices are sparse. Now, when you compute an LU factorization of a sparse matrix, the L and U factors may not necessarily be as sparse as A themselves. It depends on the structure of a matrix. But what you can do is make this an approximate LU factorization of A, where L and U are required to have a certain level of sparsity, even if a true L and U would not be so sparse. So this is called, whoops, sorry, Billy. Yeah. Incomplete LU factorization. So here's an example. Suppose what you decide to do is you go ahead and compute the actual LU factorization of A, Gauss elimination, but certain entries of A, if they're smaller than a certain threshold, you ignore them. You treat them as 0. So that's something that would have the effect of making these factors artificially sparse. But if you're neglecting small entries, then these should still be a decent approximation of a true LU factors. So this idea of an incomplete LU factorization could still give a viable preconditioner. For symmetric positive definite matrices, there's an idea like this. It's called incomplete Cholesky. In MATLAB, there's a function LU, so it's lowercase l, LU inc. Helps you get a incomplete LU factorization. There are many, many approaches to incomplete LU. So that manifests itself in the arguments that you could pass to LU inc. Okay. Okay. All right, so that's really all I have to say about direct methods. So now, during whatever time I have left, and this might spill over into next week, we'll talk about iterative methods, which are particularly useful for large sparse matrices like the kind that come up in this class. So first type of iterative method, so stationary iterative methods. All right. So these I cover in 461, 561, not in 610. I cover the other iterative methods in 610. Okay. So here's what I can do. Starting from AX equals B, I can X equals, I'm going to add X to both sides. Again, I move AX to the other side. So then I can factor out an X on the right here. Now, so if I call this right-hand side a function, I'll call g of x. Right, so g of x is defined by this formula. Then I have x equals g of x. And what that means, another way of putting it is x is a fixed point or stationary point of a function g. All right. Now, fixed point theory is something extremely important when it comes to solving all kinds of equations, mainly nonlinear equations. This is a linear equation. Where if you have some equation you want to solve, say f of x equals 0, what you can do is rewrite that as a equation of form x equals g of x, where g can be various things that are based on the original function f. And you think, well, why does that help? It's because there's a lot of theory about when a function has a fixed point. When is that fixed point unique? how rapidly will some iteration, if I make an initial guess of x that will not satisfy this, but I plug my guess in here and get a new guess. So I can solve by what is called fixed point iteration. X, k plus 1 is equal to g of xk. So I substitute the old guess into g and get a new guess. The new guess gets plugged in. The successive substitution. And a lot of very difficult equations can be shown to have a solution by expressing them as a fixed point equation of this form and then carrying out this iteration. For example, proving that certain first-order differential equations have a unique solution is accomplished by fixed point iteration. The iterates are called the Picard iterates. No relation to Star Trek. So it's a very powerful theory for working with otherwise very difficult equations to express them in fixed point form. This will actually be covered in, you'll see this week, next week, in 560. You unfortunately missed a boat. No, because the year you took 460, I covered it in 461, which is a departure from usual practice. So, we'll deal. Oh, you just read chapter 10 of my book sometime when you're bored. Okay. So in this case, with this iteration, I have x k plus 1 is equal to identity minus a xk plus b. So presumably, I could make an initial guess at x, like maybe the 0 vector, and plug that in here and get x1. Then plug that one in here and get x2. And maybe these x's will converge to the solution of ax equals b. But I don't know yet if that's actually going to happen. Or if there's going to be some conditions on it. Okay. So what happened here is a splitting of A. So A is equal to identity minus A. So one of these matrices goes here on the right side, the other matrix stays on the left. And we'll see other splittings of A as I talk about various iterative methods. So stationary iterative methods are all based on some kind of splitting of A. A is equal to m minus n. And the particular choice of m and n defines it's a certain iterative method. Okay. So now what I want to do is, because notice here, there's no matrix inversion involved. I don't have to solve any system. So the work involved here is this matrix vector multiplication, very straightforward. Each iteration takes order n squared operation, so it's cheap. If the iteration converges fast enough. If I have to take a gazillion iterations, then that's not so efficient after all. But I have some leeway here because this is so efficient. I want to make this converge, make sure it converges, and also try to make it converge rapidly. So I'm going to use preconditioning that I was just talking about. Okay. So I can apply this iteration not to ax equals b, going to apply it to this system, A P inverse Y is equal to B. So this is right preconditioning, where Px is equal to Y. So that's how the solution I really want is related to the solution of this preconditioned system. So I'm going to iterate on Y, and where I see A in there, I'm going to replace it with AP inverse. So I have Y, K plus 1, is equal to identity minus AP inverse YK plus B. Okay. And then see what I can do with that. Now, this is troubling. Actually, this looks flat out wrong. What the hell happened? All right, I'm just going to go with this. And maybe there's something wrong on my paper, but once it's on the board, it'll work out better. I hope so. Okay. What this calls for is multiplying both sides of the left by P. So P YK plus 1 is equal to P in here minus PA inverse YK plus no, I don't want to do that. Okay. All right. Might as well just wait writing something down until I give you all clear. Sorry. Okay. Now, Px is equal to Y. That means that Y is equal to, X is equal to P inverse Y. Okay. Okay. All right. So Y, so this is just equal to Pxk plus 1, just because of this relationship right here. Okay. Now over here, I'm going to make the same substitution over here. Yk is Pxk. Oh, okay. So what is on my paper is correct.
Why were you able to rewrite Y as X?
Because so for the solution, Y is Px.
Okay. Yes.
All right. Yeah. For some reason, I thought I'd be like multiplying both sides by something, but no, it's not that. It's Monday. Okay. Now, what I'm going to do is take this P right here and distribute it through what's in parentheses. So that's going to give me P minus A P inverse P. But the P inverse and P cancel. So I have P minus A xk plus B. All right. So now.
And you got that set by doing what? By
distributing a P through here. So I get A P inverse P.
Right.
Yeah. Okay. Now, the next thing I'm going to do is I can take the PXK part, move it to the other side. So I have P xk plus 1 minus xk. And then on the right side, I still have B minus AXK. Now, well, this condenses to this system, P dk is equal to RK, where dk is just the difference between consecutive iterators. It's the step from each iterate to the next one.
It's like H.
Kinda, yeah. Yeah, I see it would be a difference of x's, but yeah. Well, except what you're thinking of is x's are equally spaced, and these are not. Okay, and RK is B minus AXK. Does anyone know or remember what is this vector called? Because if this was the exact solution, it'd be 0. But when xk is an approximate solution, this turns out to be non-zero, hopefully small. But this vector has a certain name. No. All right. Starts with an R. Residual. Okay. And residual comes up in a lot of, well, yeah, many methods. Actually, all kinds of methods for x equals b. Direct, stationary, iterative, and non-stationary. Okay. Okay. So this gives us a general framework for stationary iterative methods. So I'll write out the general algorithm. All right, so first you have to choose initial guess. All right. If you don't really have any particular criteria that helps you choose, you can always set it equals 0. There are certain cases when I talk about time-dependent PDEs where there actually is a logical choice for an initial guess. That'd actually be fairly accurate. That would certainly help convergence. Okay, so then once you have your initial guess, you repeat the following until you've seen that your iterates are converged. Okay, so it's just a 3-step process. First, you compute the residual of your latest x. All right, so initially, k, the index, will be 0. All right. So once you have the residual, then you solve this system. P dk is equal to rk. So this is why I mentioned that when you're preconditioning, systems involving P must be easy to solve. because we're solving this kind of system every single iteration. If P was just as hard to work with as A, we'd have a terribly inefficient algorithm. And finally, your new x is equal to your old x plus dk. And then k will be equal to k plus 1. And then you're just going to keep going until your x's are close enough that you can declare the iteration converged, if it converges, which is not assured. Questions about? Okay. So there's two more things I want to squeeze into 12 minutes. Indicating when this converges, and also certain examples that we can choose for P. Because I haven't given you any criteria for choosing P. We like P to be close to A, but we also like P to be close to identity. So I'll give some specific ones that are effective, at least for certain types of problems. Okay, so about convergence. Let the error, which I'll call EK, be equal to the exact solution minus XK. So what I'd like to do is find out what happens to the error from one iteration to the next. So in other words, how does EK plus 1 relate to EK? So EK plus 1 is x minus xk plus 1. But xk plus 1, I can write in terms of that. That's equal to xk plus dk, but dk is equal to P inverse rk, which is b minus axk. So to unravel all this, that's rk, that is dk, and that's what's added on to xk to get xk plus 1. All right, so now it's time to do a whole lot of multiplying out. Okay, so now I have x minus xk minus P inverse B, and then I have minus minus makes a plus P inverse A xk. Now, x minus xk is ek. So that's good, because I do want a relationship between ek plus 1 and ek. But now I've got to sort out the rest of this. Now, b is the same as ax. Right. But now I have P inverse A common to both terms. So I'll factor it out. Minus P inverse A x minus xk, which is ek again. Well, that's nice. So I get ek minus P inverse A EK. But now I can factor EK out to the right. So I have identity minus P inverse A times EK. So that's how each error depends on the previous error, multiplying by identity minus P inverse A. And that tells us when convergence happens. Okay. So the iteration converges if and only if it's the best way to write this. Rho of P inverse A is less than 1, where rho, that's the Greek letter rho, of P inverse A, that is called the spectral radius of P inverse A. Now, what is the spectral radius? So for a general matrix, so I'll call C, that is equal to the maximum absolute value of all the eigenvalues of a matrix. Okay. So in other words, all eigenvalues of P inverse A, I just totally messed that up. It's not P inverse A. It's identity minus P inverse A. Okay. Dang it. Which makes sense because we want P to be approximately A. If P was equal to A, we'd have 0. Okay, so all eigenvalues of this matrix must be strictly less than 1 in absolute value. And the closer they can be to 0, the better, because that means the iteration will converge faster. So a spectral radius of 0.01, for instance, would be far more desirable than 0.9, because that spectral radius is basically the factor that the error is multiplied by from iteration to iteration. That's why it has to be less than 1. If even one eigenvalue is larger, then the iteration could easily diverge. It still might not, but you want to guarantee. So, okay. Now, I have an if and only if here. That means it's a necessary and sufficient condition. There's a sufficient condition that is similar to state the norm of identity minus P inverse A strictly less than 1. That would work too. The spectral radius is always less than or equal to any matrix norm. Okay. Now, I only have 4 minutes left. All right, so that's the condition for convergence. A few specific examples of choices of P. I can choose P equal to D, the diagonal part of the matrix. That is called the Jacobi method. And then P equals...
Is this P like from P inverse or is this P like rho? Or
P.
are they the same?
No,
Are they different?
that's definitely not the same. I'm going to exaggerate this. The row.
So that's P from.
A preconditioner.
Okay.
Yeah, over here. This P is a preconditioner that we use, the right preconditioner. So if we use a preconditioner to just be the diagonal part of A, then that becomes a Jacobi method. If P is equal to D plus L, that is the Gauss-Seidel method. These methods are normally covered in 461, 561. And then there's one more. P is equal to D plus some parameter omega times L. That is called SOR, which stands for successive over-relaxation.
Sounds nice.
What?
Sounds nice.
Okay. Yeah, I think we can all use some over-relaxation. Where a parameter omega has to be between 0 and 2, strictly. So like omega equals 1, that just reduces to the Gauss-Seidel method. Often for PDE cases, omega is chosen to be something greater than 1. So it's basically trying to cut to the chase faster. Now, here's something that will make all of us feel like underachievers. Successive over-relaxation, SOR, was first appeared in a student's doctoral dissertation in 1950. David Young. You can find a dissertation online. And thankfully, someone typed it up in LaTeX, so otherwise it's just too painful to read. So yeah, that's quite an accomplishment for a student. But again, there wasn't a whole lot of numerical linear algebra back then, so the playing field was kind of clear for him. So you never know what a determined student will accomplish. Okay, and generally, like in terms of for problems that we deal with, like from Poisson's equation, etc., if you can choose the right omega, this would be the best method. This is still quite good and tends to be better than this, but it's not always so clear cut at that. Like Jacobi method can be very effective, sometimes more effective than Gauss-Seidel in certain situations, both of these, they're guaranteed to converge if the matrix is symmetric, positive, definite. All of these converge. I'll make sure I have that right. If a matrix is diagonally dominant, yes, that is true. Okay, it's particularly easy to prove for Jacobi, not so much for the other ones. But we deal with symmetric positive definite from like Poisson's equation, so it's nice to have that result there. Okay, so I'm out of time. So in the next lecture, presumably Monday, I'll finish off this chapter, talk about multigrid, which is part of the last homework problems. So hopefully, we can have Wednesday to deal with homework issues. Hopefully, we can get past the finite difference stuff and into the spectral stuff. We'll just see how it goes.